So we've started off this module talking solely about the estimation and interpretation of our bivariate regression results, but I also want to talk about a different motivation that we may have now that we actually have estimated a linear model. And that's we now may want to make some prediction, and we can use the linear regression equation that we've estimated to help give us predictions for a specific value of x. And this isn't going to be perfect. There is variability around the regression line, right? So we need to construct some sort of confidence intervals or bounds around our prediction estimate. And there's two different ways that we're going to go about doing this given our purpose in prediction. So the first is we may have an individual and we're interested in if we changed a given value for that individual, what would the predicted response be? So for a chosen value of x naught, how does the outcome change? That's going to be our prediction interval. An example of this could be what is the predicted birth weight of a given individual baby who has a gestational period of 275 days. Or it could be like what is the length of a service call in which 4 components had to be repaired. The second way that we can think about generating predictions is that we just want to know what the average response is when x equals some value. And for this, we are constructing a confidence interval around a mean. Now, this sounds like a very subtle difference, but I'll give you an example, or going back to the examples that I just gave you, and show you the minor ways that we tweak our question. What is the predicted average birth weight of babies who have a gestational period of 275? That then, right, is averaging over all of what we know about babies at a gestational period of 275 to predict the average birth weight. Whereas before, we're interested in, we have information about a given baby, and now we change the birth weight by, to 275 days. How is that going to change what we would predict that baby's birth weight to be? The same can be said for the second example. What is the estimated average service time for calls that needed 4 components repaired? So again, these are subtle differences, but we're going to walk through how to construct each. And it's important to note that the questions that we're asking drive the type of interval that we want to use. So always keep that in the back of your head. One thing to note right now is that there's always going to be more variability in individual responses than an average. So these intervals are not only going to have different construction, but often they're going to be larger. And again, that's just because there's more variability, since we have less information about any given individual. So let's walk through how to actually construct an estimate of the outcome given some value of x. And the way that we're going to construct the standard error for our confidence intervals, given that we're interested in getting the estimated conditional mean, given this value of x. Now, I don't want to get into the formula too much. I'm sure you can look into the textbooks as to why it is constructed this way. Essentially, all you're doing here is you're taking the distance from the anticipated value that you want from the mean, and you're saying, I don't care if it's above or below. That's why we're squaring it. And then in the denominator, we're seeing how much all of the other observations differ from the mean, right? So for each observation, we'll have how far that away is from the mean, and we'll also have how far away our new value that we're interested in predicting is. And we're essentially just taking an average of those and standardizing it by our sigma. Now, when estimating for y bar when xi equals 0, the standard error is going to be the standard error of where the regression line goes through the y-intercept, which should make sense, right? Because that is where x equals 0. Now, one kind of stylized fact from that is that we're also going to have better prediction for the conditional mean of y given x naught when that predicted value that we're interested in is near the mean of x compared to when it's farther away. And I want you to think about that for a second and pause if you need to. Now, why is that? And that's just generally because we have more information near the center of the distribution of x, right? That's where the bulk of our x values are. And so that's where we're going to have the most confidence in our predictions. So the confidence intervals are going to be lower, or the standard errors will be lower. Now, we can easily do that in R, and I want to do an example where we're estimating the conditional mean of y given x naught, where x naught is equal to 0. So essentially what we're saying is give us the predicted value of y when x equals 0. In order to do that, I'm just creating a new data frame here in line 2, and using this new data frame with this new value here as the new data, having my model here, and saying that I want to return the standard errors in my prediction. Now I get 1.5 approximately, and I want you to think about this. Does this look familiar? Go back a couple of slides and take a look at the regression output. This totally makes sense. The estimate that we just got back was our estimate for where the regression line crosses the y-intercept at x equals 0, right? And we know that now from the estimate as well as from the prediction. So this is kind of a nice way of verifying that we are in fact getting the prediction that we anticipated. And again, the reason that this is just the brute construction of what our fitted regression line actually is, right? The estimate that we get for beta naught is where that regression line crosses the y-intercept. We know that's at x equals 0. And so when we use our model to predict what y should be when x equals 0, we should get back the y-intercept. To prove to you that the standard errors are actually going to change for every given value of x, now I want you to think about, and again, that's due to the fact that we have more certainty around the center of the distribution of x. Let's choose a value that's closer to that center of the distribution, whereas x equals 0 is farther away. So if our selected value for x naught is now 0.5, which is approximately the mean value of x, and we do that same prediction, and then we look at the estimated standard errors around these two predicted points. Before, when we were looking at x naught equals 0, the standard errors around our predicted value were much larger at around 0.2, whereas when we did it again and our x naught was 0.5, the standard errors around our predicted value were much smaller. They were under 0.1. And what's interesting is that, and I didn't really show you what the prediction was here, but the prediction doesn't really change. The standard errors and our certainty around that are just smaller. And again, that's because we're getting closer to the distribution of x, right? Like we've got more information about it. We have better confidence in predicting the conditional mean of y at x equals 5 because that is literally the center of our data. So when we finally report what the confidence interval is around our predicted value, we're going to report it in the exact same way as before, where we multiply the standard error of our predicted value by some t statistic, and that's going to be derived based on the degrees of freedom. So what we can do here is really nice. In R, this allows us to just put in what type of interval we want. So we're going to say we want a confidence interval, remember, not a prediction interval. We can tell it what our alpha is. In this case, the critical value is 0.05, aka we want 95% confidence intervals around our predicted value. And what this returns is the predicted value first, the lower bound of the confidence interval, and then the upper bound of the confidence interval.